Okay, let's start. So may I start? Yeah. So this is an invited lecture. So I work in Nokia Bell Labs, the research arm of Nokia. And today I want to talk about zero-knowledge proofs, SNARKS, and applications of this technology for you. So how many of you are familiar? You heard about zero-knowledge proofs? I mean, many of you. SNARKS? Heard of it? Okay, but today I hope I can give you some good understanding of this technology and also show you the applications. They are very useful, especially in blockchain, but also outside of the blockchain context. But today I don't talk about blockchain at all. We try to understand the concepts, how it works, what are the promises, and what we can do with it in real world and what people has done already. So I work in COSIC as well in Leuven. So I'm partly in Leuven, partly in Nokia Bell Labs. So you will see a notion of both. So as I said, I think I introduced myself, so I don't need to introduce further. And what we do at Bell Labs, if you're curious, and Nokia, is that we don't produce phones anymore. We are working on future networks like 5G, 6G, and things like that. And currently, Nokia, in our team, we're working on zero-knowledge proofs, homomorphic encryption to design privacy-preserving protocols and make impossible things happen. So today we've talked about cool topics. Yeah. So first I want to give you some intro, what it is exactly, how it works, the fundamentals. So there is this picture, it's a famous picture. There is a cat in this picture. Can you see the cat? Can you spot it? It's not easy, but I know that I really don't want you to find the cat, but imagine that I claim that I know where the cat is. I know where the cat is, but you tell me, but I might lie, no? You tell me, prove it to me. Tell me that you know where the cat is. So you think that this is a paper, picture printed on paper. You give me scissors, and then I'm cutting that picture of cat. It's visible? Yeah, it's visible. So this is the cat, and I tell you there is a cat, but it's still, so it means that I know some coordinates in this big picture, but think this picture is huge, gigantic, like size of the Earth, for example. But I have the coordinates of this cat, I know where it is. So there's a property called completeness. So if I know the coordinate, I could convince you, right? If I could crop the picture of the cat and give it to you, and you would be convinced. I know it because I did it in front of you, but maybe just connect to yours. Okay, we had a technical issue here. So I could just like turn back, crop it, and you're sure I did that. And so if I know it, I can convince you. So if I know the secret coordinates, I can convince you. This property is called completeness. So it's very clear. And soundness comes from the fact that if I didn't know the coordinates, I couldn't crop it, so I couldn't convince you. So if someone who's proving something to you, if that person doesn't know that secret, cannot convince you. So this comes from soundness. So there's, for example, a probability. They say that very unlikely that that person can convince me because he couldn't crop, right? What I wrote here. If you don't know the coordinates, whatever you do, whatever you crop, you cannot convince me. I could crop something else and tell this is a cat. You would say, no, I see, this is not a cat. So you don't know the coordinates. And the zero knowledge comes from here, that I, without showing you the coordinates, could prove to you that I know the location of the cat. It's a very simple example. And this is a proof of knowledge also, because it's not just a proof that I know something. I know exactly there is a cat with these features, that there is a coordinate somewhere. I don't tell you the coordinates, that's the proof. So these are called interactive. There's a class of proofs called interactive proofs. I want to generalize what I said. So they typically involve a couple of interactions between the prover and the verifier. Normally in my pictures, on the left side, we have the prover, someone who wants to prove that, that he or she knows something. On the right side is like the verifier who wants to make sure that I really knew the proof. So they have to, there's a certain set of messages that are exchanged. Like first there's a commitment, that, for example, I say, I claim that I know the coordinate of the cat, and then you say, prove it to me. And there's a challenge, then that you challenge me, and then I crop and I send you the picture, and then you can verify that was really, that belongs to that paper. And there are ways of verification. But we will see a concrete example with numbers, you know. If I claim that I know a number, blah, 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 we will see in the next slide. So this was completeness, if I want to review again. So completeness, if the prover is honest, the honest verifier always accepts the proof. So if I am honest and I provide the proof, you will be convinced and I really know the secret. And soundness is that I cannot cheat. If I don't know it, I cannot provide the proof that you will be convinced. And a special soundness is a special type of soundness. It means that I knew some secret information. And if I didn't know that secret information, I couldn't convince you. So this is slightly different than just the soundness. Because soundness, I can say that a statement is correct. Like, there is a cat, but in this one I say, I know exact cat, a piece of information. Yeah, there's a little difference in this. So these are the terms that you will see in the literature. If you read a book or article about zero knowledge, you will see this. One of the famous protocols is the Schnorr protocol. So Schnorr invented this many years ago. It is called sigma protocol as well because the exchanges of messages that looks like a sigma, doesn't matter. So Alice, or the person on the left side, knows the secret, knows W. W is a witness. They call it witness. So it's a secret. So she calculates G to the W, so it's a discrete log problem, and send that, and that's a public statement. So she says that this is the witness and this is the commitment to my witness. This is this value G to the W, and it's a public statement. And she claims that she knows a value W that's a solution to this equation. That's a discrete log solution. So that's G to the W. So she wants to prove this to Bob on the right side without showing Bob that she knows W. But you might say, well, what for? But that can be an example of this can be, imagine you want to buy alcohol, for example, there's an age limit. Then in some countries, for example, is 18. Then you can show your ID card to the supermarket and say that I am older than 18. Then they can see your birth date, in fact. But you don't want to show your birthday, but you want to prove that you are older than 18 without showing your birth date. So you can create privacy-preserving protocols using this zero-knowledge stuff. So this could be that date of birth, but you want to prove that you have that value. So what she does is that, this is how Schnorr designed the system. So Alice generates a random value R from ZQ. ZQ, I assume you know what it means, right? You know? So it's like from 1 to Q, like all integers, the ring of integers from 1 to Q. So it's a big set, generates a random value R. So she computes G to the R, and she sends A to Bob. So Bob doesn't know R. It's a commitment. As I said in the previous slide, there's a commit and challenge. So Bob randomly samples C from 1 or 0. Usually they choose 1 and 0. To challenge Alice. Alice calculates this equation. So the R that she knows, and C times W. W is the actual witness we have that she wants to prove. So she calculates Z, and she sends Z to Bob. But Z is random, right? Because R was random, and Bob doesn't know R. So this value Z is completely random value to Bob. So what he sees is that some A came, doesn't know what is R, he sends C, and we got Z. So it's just completely random looking values. So by computing this, Bob can be convinced that Alice actually knew W, otherwise he couldn't do that. You might say, how? But if you open this, you will see. So Z was R plus CW, which is equal to G. A was G power of G to the R, and X was G to W, and it's clear, right? So Alice couldn't create this if she didn't have the value W. She couldn't create Z. So Bob is convinced that Alice is aware of W, which corresponds to that public statement, that public commitment, because he is using that value X also to create this equality testing. Is it clear? Right, so he knew that. But there are a lot of challenges here. But first, we want to see a special soundness. So to do that, a special soundness, we want to know that special soundness was about the fact that we want to know the prover really knows that secret. Like if there's secret W, they really know that secret. So if you know something, some secret, in real world, I should be able to extract it from you, right? If I can force you to give it to me, I can convince you to tell it to me. But if you don't know that secret, you cannot give it to me. But in the security proof of this, if you want to prove that this scheme is secure, or if you want a proof of knowledge, proof that this scheme has proof of knowledge, so it means that this theoretical adversary should be able to somehow manipulate, cheat in the game of this protocol and extract that secret value. If we cannot write an extractor to extract that value, it means that we don't have, it means that the proof is wrong. So Alice didn't have actually W. So imagine we have two valid tuples. So these are like, we can assume that the prover can answer to two queries for the same A. You see that? That we have 2 times A. Oh, I think, is this correct? Okay. We have 2 times A. It's the 2 times repetition of the protocol. So we have Z1 and Z2 because R is the same, A is the same, and we have 2 different C samples because it's 2 times run of the protocol after the first commitment message. We are cheating right now. We want to be able to extract the witness. That's the whole idea. So imagine that the adversary or the extractor that we are writing has these 2 views of the protocol based on the same A. So we can divide. We have this equality, right? We can divide these 2, come up with this equation. We can simplify this. And if you see, we can actually calculate W. We could extract it. And why W works? Z, if you see the formula of Z, I mean, you can read it yourself later. The formula of Z depends on, this equation depends on values of Z, which are public values. These are public values that are exchanged in the protocol. And C's are also public values. They are sent to the, created by the verifier, sent to the prover. So based on these public values, we could, in fact, come up with a value of W. So we somehow were able to extract this. This is theoretical. This is for not a proof of knowledge soundness. So as I said, like, if you know something, I can convince you to give it to me. So this is a method of extraction. I can beat you to give me the secrets, but this is a way that we can fetch a secret. We can prove that there is a knowledge soundness in this protocol. But there is another thing. How sound is that? Because if you look at the protocol, C was 0 or 1. If C is selected as 0, so it means that Z will be just R, right? C will be 0 and Z will be R. But then a cheating adversary, a cheating prover who didn't have W actually, in fact, could complete this protocol and this equation would hold, right? So this is not good. And how often this happens is 1/2, right? The probability that we might get 0. But if it was 1, then it was R plus W, then Alice must have W to be able to do that. So this is not sound enough. So it means that with the probability 1/2, in fact, the malicious prover could convince Bob that she knows W. So how to solve this? We have to repeat the protocol a lot of times. We have to repeat that this 1/2 probability becomes smaller and smaller and smaller. That guessing the value of C would be really difficult. So in this way, we can increase the soundness. So usually they say lambda times, we repeat this. Or another way is to, for C, we could have a different domain, not 0 and 1, we could have a bigger domain for soundness. Yeah, this is another thing. So, but in real world, having this interaction to prove something, if I go to supermarket, I want to show my ID card, I just want to give the proof and the person sees the proof and convinced. We want to reduce this interaction. This is not good. We want to have non-interactive scheme. We want to have like, with one shot, give the proof. So there is a transformation to convert this to non-interactive zero-knowledge proof, which is abbreviated to NIZK. You might see NIZK a lot in the papers, everywhere. This transformation, which is very famous, is invented by Fiat and Shamir, so it's famous as Fiat Shamir. So what you do is that basically in this protocol, we can use a random oracle. A random oracle can be a hash function. If you have a good hash function like SHA-2 or SHA-3, we can use that to actually calculate the random values that the verifier was supposed to give us, like C. You can see, I give you an example. So we had R, we had A from the protocol, and we could calculate, we could feed G to the R and G to the W to the hash function and produce C. And that would be sufficient enough in a random oracle model. Then we could, when we are creating Z, we just use that C. And later we send Z as our proof to the verifier, and verifier could check that equation that we have, the equality testing, and also the verifier could check the hash, that you did the hash correctly. In order to make verifier be able to check that hash, that you did the hash correctly, it means that we have to use all public values to generate this hash. So if you see G to the R, G to the W, they're public values. They're not like, we didn't use the value R. That's why they say that you can use it when the protocol is public coin. Public coin means that when you have this public randomness is exchanged. But this was a side note for you to know that this can be done, can be made non-interactive. But in this way, it will be completely non-interactive. Yeah, I explained this. Now, I want to talk about the SNARKS. So you might think, what is a SNARK? I mean, you probably heard it. I mean, I don't know if you heard it or not. But a SNARK take this concept of zero knowledge and take it to another level. Before starting the whole number of slides that I'm going to present, I can tell you what it is. A SNARK is extending this concept to provide verifiable computation. So imagine that there is a piece of software that is executing something and produce an output. When it produces an output, it can produce also a proof that execution was done correctly. Like, it's very useful. I will show you a lot of applications. This is really exciting area of business, app research, whatever. We can do a lot of things. I will show you. It's really interesting. So, so to repeat what it is, so it's and you might think also, what's the relation to zero-knowledge proof? So you execute a program, you can provide a proof that this program executed correctly. But the program that you execute might have some inputs, right? There's input to some values you give, some data you give it to that program to execute. But that input could be private. you don't want to put it in the proof, because that proof, to verify it, you need to have some of the inputs. But if there's a private input, you won't provide it. So that means that that proof can be verified, meaning that the program executed correctly given some inputs, which I don't know. I will come to some real-world examples to understand. I just wanted to have some intuition what it is, a SNARK. So SNARK alone provides only verifiable computation, that you can verify computation is done correctly. They call it also computational integrity. ZK SNARK is about the fact that we might have some extra input that they call it witness, like previous protocol. So we can see from a practical point of view, just want to see what time is it? Where can I see the time? Okay. So the program gets some inputs and produce output. This is a regular program that we have. But when the program is executed, over the course of execution, it has some values written in the memory, some values are in registers, and you do some, there are variables, right, in your program. So there are some intermediate values in that. We call that intermediate values, all of them, over the execution, course of execution of a program, a computation trace. So everyone can actually see the computation trace. You can just log. So if we take the computation trace and the input and the output of the program and giving to a SNARK, if you give it to a SNARK engine and you provide what constraint you have, constraints are like the requirements of the correctness of the program. Like if you have a Fibonacci sequence, you have two numbers, you're adding them, put in the third number, then you add them again. So what a constraint could be that two consecutive number has to be added, every number is equal to the previous two consecutive numbers. So this is a constraint. You have to check this. You have to check that these additions are done correctly. This is a constraint. So every program can have some number of constraints. We can think of it as a requirement that the program is executed correctly. And if you have the computation trace, exactly for the example of Fibonacci, if you take two numbers and start the Fibonacci calculation, if you do it 1,000 times, so there are intermediate values that you are calculating. That's intermediate values in the variables. They're called computation trace. And then you have an output. Yeah. Then you can say that the output has to be this also, if you did that correctly. Then you get a proof of execution. And the verifier will take the proof, takes the inputs and the constraints, and can verify. And what is important about the SNARK is that, because one way to verify that is to recalculate the Fibonacci trace, right? Just calculate it again and check that, okay, you did it correctly, I did it myself again as a verifier, and it's correct. But this is not very interesting. The interesting part is that if we can actually verify in a very fast way, like real logarithmic, like not going through the entire computation again. Like the computation might take an hour, but verification should take milliseconds, like quickly that we can verify. This is a property used in blockchain. I will explain how and where. So this is actually defining what a SNARK is. So a SNARK has to be small. The proof that you provide also should be very small. It shouldn't be very big, because you can have the entire computation trace as a proof. You don't want that. You want to have something very small, tiny, and then proof also is fast. So the proof verification should be fast, but the proof generation is not necessarily always fast. It can be slow. It's good if it's fast, but in practice it's not really fast. Yeah. And the inputs, if you don't want to have the inputs for verifier, then it's ZK SNARK. That's the zero knowledgeness comes from here. Also, the computation trace, that you are not using computation trace for the verification, that also might have a lot of sensitive data in it. You don't want to show that also. That's part of zero knowledge, that there was a computation trace, that this proof was generated and then is verifiable. Okay, and examples, as I said, the ID card, which is redacted, like the date of birth that you have, can convince people, or in blockchain rollups that I'm going to explain right now, or in zero knowledge machine learning. So for machine learning, you might have I will have examples later, but remember this exists in sensors, telemetry, in journalism. It has applications. So you might think, well, how it is useful in blockchain, and how much you are familiar with blockchain, with blocks and, what are you? Okay. So every time we have a bunch of blocks, I'm not very familiar myself. So except if there is mistake, but I want to explain how SNARKs can be useful to actually speed up something, like something very compute intensive. So when we have a bunch of blocks in blockchain, there are a lot of new transactions. We want to check that these transactions are correct. We have to check some signatures, hashes, and all these things. And usually miners or validators are doing that. So all of them, they have to do that, and they have to run a consensus protocol. Each of them individually do that, and then does that. And then they run a consensus protocol that, was it correct? And everyone said, yeah, it was correct with certain probability that they have. They said, okay, that was good, and then we create a new block. Yeah, all these transactions are packed in a block, and the block is added to the blockchain. This is happening, and this is very resource intensive, because all of them, they have to check those signatures, and at the same time, they should run a consensus protocol. But in fact, and they can say accept or reject the block, but in fact, they could give it to some random person, someone that they don't even trust. And that person, I'm talking about an alternative approach. That person would check the signatures and all the correctness of all those transactions. That this time, for example, someone had enough funds that could transfer, this is correct transaction. And that person would use a SNARK to provide the proof that he checked everything correctly. Like, he checks it one time and he provides a proof that he checked it correctly. He gives the proof to these people, to these validators. And validators, as I said, the proof is small, and also it has to be really fast, regardless of your computation size. It can be very huge computation size. They just need to verify that that guy, red guy, checked the transactions correctly. And if they're convinced, they say, okay, he did it correctly, we create a new block and we add it to the blockchain. So this is used, this is called rollup. I think probably you heard it if you're interested about blockchains. So they call this a scalability solution for blockchain to speed up the creation of blocks. So you didn't have to, the validators didn't have to create all these blocks and check all the transactions, validity of transactions, and they just needed to check this little proof, which was, the verification was super fast, and he did that. So you see, it's not just about privacy. In fact, here there is no privacy. It's not about privacy, but it is one of the applications of this. So as I come back to this slide, not come back, actually I come for the first time to this slide, with a SNARK we can actually solve a scalability solutions. If there is something is slow and has to be done by many people, one person can do it and convince the others that I did it correctly, provide the proof, and then they cheaply verify that the computation was done honestly, or the privacy things, like maybe there are some sensitive inputs and then someone has to compute something, we don't trust it, maybe it's a device or sensor which is sensing temperature in this room, but temperature or this type of things, if it is at home, these are considered sensitive data, right? But then they can aggregate these temperatures, readings, and calculate an average and send it to some other service that we are using. But that service is interested in the averages, but doesn't care about the individual values. But also, that service might not trust your aggregation at home. So he can calculate the average, provide the proof that we did the calculation correctly, and this third party will get the proof and the average. It will never know what was the temperature, but it can verify that the average calculation was done correctly. So there is more trustworthiness in the system. There are like a lot of proof systems today. I mean, this is like copy from Wikipedia, and then there are many of them based on different cryptographic assumptions. You don't need to know them, but I just want to say that if you haven't heard about them, if today you know this concept, and then look at like the job market, and you will see like there are like tons of positions for just this. And this is just a tip of an iceberg. There are like hundreds of companies working on this today. And there are many protocols. So I was thinking about, maybe still a little bit more formal. So there's a class of this, very popular class of this SNARKS, ZK SNARKS, that they have this functionality. We have a prover, we have a verifier. I think you've seen this. On top, you can see that there is a setup phase that takes the circuit. But have you had courses like multi-party computation, or are you familiar with circuits when I'm saying circuits? Right? Circuit is, your program you can think of it as circuit. Every program can be written with circuits of ands and additions and everything, right? Computer actually does that. You compile it to some circuit. So in this area, when we say program, we think of it as a circuit. More lower level, but you will see more high level things later. So you have the circuit of your program. In the setup time, we create two types of keys. First key is a proving key. When you want to generate a proof of computation, we need this proving key, and also the verification key. When we want to verify, we have to use this verification key for verification. And the P is the prover, which takes the proving key. X is a public value that can be input to a protocol, which is public inputs. And W is the witness, is the secret that we had. We don't want to share with anyone, but that's useful for the computation, and we provide the proof. We generate the proof. And for verification, we have the proof, the public value, and the proving key we can accept or reject. So this is the flow. So the prover takes proving key, X, W, and then it's clear. So the proving has to be short. That's why they call it the SNARK, is a succinct. Succinct means small, tiny, fast. Argument of knowledge. So it's like has to be short. The proof has to be small, and also verification has to be very fast. This is the property. And it's logarithmic in the size of the circuit, because it has to read the circuit anyway, the circuit you have. And also the verification time has to be also logarithmic, and X is the input, because it has to read the input. You cannot do that without reading the input. If the input is larger than log of C, and then yeah, but it has to be logarithmic. That's the message. That means it's small and also fast, regardless of the size of your actual circuit. Related, but it's much, much, much smaller than actual size. The circuit can be huge. If a modern program, if you compile it, you will see you will have millions of trillions of gates if you write a circuit. It's vague. I'm going to show you some concrete examples. So let's learn it by doing it. So I want to show you right now very popular, one of very popular proof systems, ZK proof system, the SNARKS system, that was published like 10 years ago. But it was, in fact, I think one of the first practical schemes that could provide this verifiable computation and zero knowledge proof at the same time. So, and I want to show you, if we have a program, how we can convert this circuit to a proof and how we can verify it. You will see the flow. So bear with me. This is the last thing, which is a little wonky, and then after that it will be applications and it's fun. Okay. The right one. Okay, so if you have a computation, if you have a program, we cannot just apply zero knowledge to it. So we have to first transform your program to some format, they call it arithmetization, to some algebraic form, algebraic circuit, and then do these steps. I will tell you what are these steps. This is just some overview before explaining something complex. What is not really complex, it just has many steps, but very simple steps, but a lot of them. So imagine we have this equation there. It's our program, and we want to prove that we know the solution to this equation, right? The solution is 3, for example. We know this. But in real world, it would be a gigantic equation. I wanted to convince you that I know the solution to this equation, and then I take a small one because I can draw everything on the slides for you to see what's going on. And we have a field of 41. 41 is our prime number, so it means that every value in this circuit has to be smaller than 41, like Galois field 41. It's like the ZQ we had. Yeah. So this could be the program, right? You all programmed, right? It's not like you haven't seen program, so I assume you know what it is. This is Python program. We have the evaluate function, which takes x and, much better, and we can input x and it would calculate exactly x to the 3 plus x plus 5. But in order to be able to write proofs for this, as I said, we have to transform this to some other format, right? So what we do is that we try to, we transform it to quadratic form. So it means that on the left side, we will have only one variables. That's not natural. We define these variables in a way that on the right-hand side, we have maximum only one multiplication, but we can have many additions, as many as you want. So I transformed that program to this. These are equivalent. I just flatten this. If you look at it like x multiply x, I create a new variable, var1, to multiply. It's exactly the same circuit. But if you write this as a circuit of additions and multiplications, we will have this circuit that you can see on the right side. It's clear, right? Okay. So we have 4 gates. Look at the circuit, don't look at the code anymore. We have 4 gates, 5 variables, and 1 constant value, right? 5 added on top. Okay. So x can be anything, and it's our input. If you remember, I wrote it on top. This is the process we are taking. We have a computation, we flatten it, we have an algebraic circuit. Now we want to create the rank 1 constraint system. It's a format. What it is like a bunch of matrices. I'm going to show you right now. I want to encode my circuit somehow into these matrices that I can check some equality later. You will see. And these matrices are there. A.S multiply B.S equal to C.S. You might think, what is S? I will come back to that. S is, if you run this circuit, all these wires in the circuit will have a value, right? S is the value of, when you run it one time, if you put 3 here for x, var1 will be 9, and then they will have other values. It's a vector of values for each variable, and that would be our S. You will see. I explained it actually, I should have shown you this. So, that is, first one is 1 because it's representing constant, but it's a convention, forget that one. So we have these wire values. We have x as a wire value, we have out, which is the output of the circuit on top. We have var1, var2, var3, right? These are, if you run this program, you will have one instance of this value. There will be values for these wires. And we call this our witness. Actually, this is very, if you run a program, it's a memory of your program, like what's happening in your program. You don't want to show it to someone. And we want to create proofs based on that. But we need to have some encoding of the program first. Just forget S for now. I want to encode this circuit into these matrices. Just a question, has any of you seen this type of things before? Or is new? Okay. So what we do, we have columns here, as you can see. The columns are like representing 1, x, out, var1, var2, for 3 of them. And the left A, think of a gate. We have a left input and the right input and the output, right? So this is the value for the left input of the gate, right output of a gate, and the output of a gate. So for the first gate, this one, gate number 1, we have x, of course, only x is coming in for both direction, x, and output is var1. Clear, right? And then for the second gate, we have var1, x, and var2. The second gate is addition. Addition is slightly different in rank 1 R1CS. We have to, both inputs are in one row in, this is convention, in the left matrix. So it will be x and var2. And here on the right side, we say constant because this is considered to be a constant. We put 1, but just accept it. And the output is var3. And the same for the last gate, we have 5. we put value 5 because it's a constant value, and var 3, which comes in, again is addition, and then we say 1 is 1, and the output is out. We somehow encoded this program into these 3 matrices of input, output, and blah, blah, blah. And this is our instance, for example, if we say x is equal to 3, if you compute with these values. And that equation will hold. I will show you right now in the next slide. If you have a dot s, that's, I think, dot product. And then minus that one, that holds for that instance. So if someone wants to say that, look at this s vector, but in fact cheats that person and choose different values there that is not really corresponding to the computation, that equation won't hold. That doesn't work. So we had this. I just moved everything on top. Nothing fancy here. So I want to show you that equation. I mean, for one row, that this is actually working. This equation works. You can see that. It's 5 to 1. I just made it vertical. Multiply s. Do you see my mouse? Here. So this is 35 if you just multiply. It's like a dot product. And this is 1. This is for this row, this column, this row. And for this row is this one, is 35 is equal to 0. If you repeat this for all rows, it will be 0. And if we had a different S, different execution, different wire values that was not within this circuit, this wouldn't work. Now, it is still very hard. So it means that to prove that this is correct, we have to really run this, check this matrix multiplication, but this doesn't scale. Because in reality, I compiled myself, for example, for some average size programs, these matrices, they have like millions of rows, even sometimes trillions of rows. So this is really not scalable because we want to have SNARK to prove very fast, right, quickly. But this wouldn't work. We have to do still more things to fix this. And every row corresponds to one gate. So whenever they say that this program, this circuit has 1,000 constraints, you have to think it has 1,000 multiplication gates. This is like how the terminology, you will see later if you go outside and see online, people talk about this. That means the number of constraints. So what we do is that we take every column and interpolate that. What it means is that let's take a first column and interpolate like this. We say that we have x and y, 1, 2, 3, 4, because these 4 gates here is a simple one. And we just interpolate this to a polynomial. You know interpolation, right? So I assume that it's just, we have 2 points. If you interpolate, it's one line, you know. So we do this, and in fact, actually, this polynomial a1 is 0 for these values, right? This is obvious, right? It's not 0, it's these values. Like a1 is 0, and a4 is 5. This is like, if you evaluate it, is this value. So what we do is that we go for every column, we generate a polynomial. We interpolate to a polynomial for these indexes exactly, 1, 2, 3, 4. So we will have as many columns as we have polynomials. A for representing the matrix A, and BIs for representing matrix B and the C. So we will have polynomials as many as the wire values we have, almost. Now there's this equation. This equation is very similar to the other one. This holds. It's almost the same. It's just like if you put, for example, P1, it will be 0, P2, 0, P3, 0, P4, 0. Because we move, any S would result in the previous slide, you saw that it was 0. Now, we in fact converted that matrix representation to polynomial representation. It's clear or not? Okay, I hope so. Okay. But you see that for these points, this equation, this px is 0. So that means that there is a polynomial like this. If you divide this, if px is divided by tx, I mean it's divisible by tx, by t. This polynomial p is divisible by t. Makes sense, right? Because in these points it is 0. Yeah? Because it was 0 in these points. We know that it is 0. Is it clear why it is 0 on these points? Yeah, okay, I hope so. And then, so this is divisible by that one. So if you divide it, what we get is another polynomial, which has a certain degree. They say it has to be low degree, but it's not like we won't have coefficients that are rational numbers. They're all, because it's divisible, we will have another polynomial. So it means that if you divide this, we will get hx, it's some polynomial, which is a smaller, or the degree is much smaller, but it's another polynomial. So p is in fact multiplication of this h times t polynomial. Yeah. But they agree only on these points, but on the other points, you never know. Just keep it up, take it, accept it, we will come back to this. So I want to explain how we can generate the proof and verify this in a very fast way. So on top, I just wrote this equation we had, and also this p, which is equal to tx and hx. T, that special shape polynomial is called vanishing polynomial. It's just a term, if you've seen. So we have 3 algorithms. As we talked before, we have the setup algorithm, which takes the circuits and creates an evaluation key and verification key. Evaluation key is that proving key. And we have the proof function, which takes our inputs, wire values, and everything, and basically S, but I didn't write S. I wrote X and W, but it takes S, and it's a mistake. It produces a proof. Maybe I'll fix it later. It produces a proof, and verify. Don't see this. And verify takes the verification key and the proof, and say accept or not, this was correct or not. So this is what I'm going to fill in the slides with. It's a little mathy here, but it's the last slide which is about math. After that, it will be just applications, and it's fun. But it's easy, it's not difficult. It's just a little bit of math. But if you don't understand, just stop me. I think it's too much. It's boring slides, or boring, or probably boring. Okay. But the slides will be available online, so you can check them later. And if you want to understand more, I mean, if you don't follow, I have to teach it because later you might want to watch it again. So we will see. We had this in previous slide, right? We have all this polynomial A's, polynomial B's, polynomial C's. We calculate them for that equation, and we have T also we calculate it. So we do that actually. In fact, I'm writing it here. We calculate that. So what we do is that we generate a random value R, and then we create the evaluation key as this. So in fact, we evaluate each of these polynomials in value R and calculate G to the power of A1, A6 for all of them. Just to create this G power of something. That's our evaluation key, and it will be used later. You will see when. And we have also G to the TR. We calculate evaluation of T by R, and we have this as verification key. We see this will be useful in verification key. In fact, somehow, what we want to do is that we have that equation on top. We want to say that at a random point R, this holds. If that holds, this random R, prover couldn't know it in advance, and it's a random point. If in a random point it works, there's a lemma for this. It means that equation is correct. This is called Schwarz-Zippel lemma, which I don't explain in my slides, so doesn't matter. But if we can prove that in a random point R, that equation is correct, then it is very likely that it is correct for all the other points. peaks, I mean, on top. But we have to do this in a zero-knowledge way, because verifier cannot have the polynomials. If we give these polynomials to verifier can create our execution trace, because this is zero knowledge. We just want to say that this was executed correctly. You don't need to know the actual trace. So that's why we are going to the g to the power of something. We use discrete log problem that verifier cannot access that. So prover will execute the function, will have generated the vector s, which we had, all the wire values. And prover has to calculate, what it does is this. It wants to calculate, as I said, that sigma si ai at point r. So what it does is that it takes from the evaluation key, g to the a1 r to the power of si, that's wire, and multiply all of them. When you multiply all of them, you will have that value, g to the value to the sigma of si ai. Okay, and then we do the same for b and c. Clear or not? I don't know. Okay, but you can watch the video later. If it's not clear, you will understand. But you should have followed. If you miss one step, you don't get what's going on here. But yeah. But if you don't get it, it wants to create that thing somehow with existing public parameters he has, and one execution like the SI, all wire values. It creates that each of those elements in that PX. And then he wants to also evaluate h, polynomial h, at point r. But he doesn't have polynomial h, but it is easy to calculate that because he has tx and he has all of this. So what it does is that divides p by x. So it has a polynomial, h0, h1, and h0. And it wants to evaluate that polynomial also on point r. So what it does is, we have also in the bottom, if you see, we have also g here, g power of r1s. We take these values and calculate the power to hi. H is the coefficients of this polynomial h. So we can have evaluation of this polynomial h at point r in the exponent of the g, there. Which is is used for that one. Okay, whatever we did, I don't know if you follow or not, but the proof is this. Proof is 4 numbers in the field, in the group. G to the power of A, evaluated at R, G to the power of B, evaluated at R, C, and H. So our proof is 4 numbers, regardless of the size of your program. This G power of something is a group element. So 4 group elements. So each group, if your group is 256 bits, it means that 4 times 256 bits is your proof size. This is the proof. And you will see how you just need to somehow check that that's correct. And this is how we verify that this is, in fact, the correct execution. So if you have millions of gates, it didn't matter. In the end, you always reach to 4 group elements. And how to verify that? For Pinocchio approach, which is this, we use bilinear pairing. Whatever it is, you will learn it in different cryptography class, but then you can just verify that this equation holds. And this equation, if you look at it, is exactly there. A, B minus C is equal to HT. And verification key was G to the T evaluated at R, which we use it here to make sure this is correct, which is initially committed. Yeah. Next slide, there is no math anymore. So I will be also available. If you don't get it, this video, you can watch it again. I think it's also in the afternoon, late afternoon. It's not fun to listen to this wonky mathematics. Okay, maybe 10 minutes break. I promise you after this it will be just fun. Really, look at the picture I have here. I have this type of slides. Trust me. But zero knowledge proof is a bit tough topic. It's not an easy topic. I chose the simplest proof system. Some papers are literally unreadable. It's a very complex system, but what they enable people to do to verify that the program executed correctly is game changer. I mean, if you see the applications, you see, okay, it can do that. Already for blockchain, it could speed up. Like instead of 100 or I don't know, 1,000 people running the same computation, one person does it and everyone just verify that was correct. So it can do a lot of cool things, but I will show you how to generate these proofs without any math also. I will show you some code with 2 lines and boom, I have a program which has proofs and you can use it. So far what we have seen was basically more about concepts and mathematical foundations of this zero knowledge proofs. Not everything, there are a lot of math involved. I just give you a tip of an iceberg how this system works. But from now on, I'm not talking about math. I'll just show you maybe some types of zero knowledge proofs and also applications, how they are, people are looking at them, how they're used or how they might be used. And I will show you one very simple code actually, how you can develop zero knowledge circuit and you can provide proofs for execution of that. It's very useful. So right now what we have seen was a circuit with very small data, right? X and Y, and X was 3. What if we are training a machine learning model? We have terabytes of data, right? So it would explode. What you have seen, the matrices would explode. You know, there would be not really practical to use. That's why actually it still is not practical. People are trying to make it practical because you will see where it is useful. But one way to do that is to, when you have this very big chunk of data, because for example, if you're, imagine you're calculating an average of all these values in 2 terabytes of data. The function you're calling is average constantly. So what if you could just chunk them into smaller pieces and you just calculate an average, provide a proof, then calculate average for the second chunk, provide the proof, and then check all the proofs are correct. And then calculate all the average of averages and you are making the problem smaller. You know, for this matrices become smaller and become fast. But there is a line of work for recursive proofs, what I said, is that you take the first chunk, give it to the prover provide the proof, but not really full-fledged proof in the second slide. Maybe first slides. And then for this, you take the second chunk, you check that the previous proof for the first chunk was correct. You do calculate the average or that function that you're calculating, which is repeating, and provide another proof. And the second proof for this third block will say that all the operations up to now were correct because it checked the proof also in a verifiable way. In fact, you check that the proof was correct in a verifiable way. So you don't need to recheck it. So you're recursively checking the previous proofs as well. You take the next chunk, you verify the previous proof and you do that. But there's still verifying a proof. The circuit of that, if you write a circuit of proof verification, is a huge circuit. It's very expensive. So there's a line of work. I started with a paper called Nova. They make this very lightweight. I don't want to go into details. Just want to say that there are recursive proofs and also iterative. They call it IVC, iterative, I forgot. This kind of lightweight verifiable proofs. So here you can in fact do this recursively, but each time that you want to generate a proof is a lightweight proof, it's not a full proof. So it's something fast and small that you just provide it to the next block and you verify that little proof was correct, which is very lightweight. And in the last step, you generate a proof that all data was computed the average on all data was computed correctly. And the last proof is a regular SNARK proof. Just wanted to give you a notion. If you see it somewhere, you know this is recursive proof, can be done recursively. If the data set is big, or if you have a stream of data coming in, you constantly want to generate proofs. Another thing that in Nokia we are actually looking into, we don't have any actual deployment, but we are exploring, is that in Industry 4.0, let's talk about other things than zero-knowledge proofs. So there are these robots. They're thinking in the future industry, in the factories, they can be robots. The robots can just go travel around the factory or this construction site, and the robot has camera, it's taking picture, constantly monitoring everything. It can go to places with very high temperature or places that are like toxic for humans to go, but they're constantly looking for anomalies. Like they're checking if like this gas, these pictures I found online, they're not real, but they can see, oh, there's an anomaly here. I see that this tank is leaking or this pipe has a leakage. They can, in fact, send these images and this data to another computing infrastructure. Say, I think there is an anomaly here. And they can check also there's an anomaly or not. And then if there is an anomaly, they can contact some technicians or the person who is responsible for that. So basically, this robot take a picture, locally does some anomaly detection with AI and machine learning, and it's a lightweight one because it has to be local. They don't have a lot of computing capacity, so they do some little lightweight anomaly detection. If the answer is yes, probably there's an anomaly, then they send the pictures to some sophisticated ML model to check whether there is an anomaly or not. So you might see what's the relation here. So I was just trying to motivate this. I noticed that manufacturing sites are the #1 cyber threat attacks. And have you heard about the Stuxnet, for example? Like it was a few years ago, 10 years ago, a long time ago, that it was a malware targeted Iranian centrifuges for nuclear research and nuclear activities, whatever they're doing. But so what they did was changing the speed of rotation of centrifuges, that it could melt them down. It just, all of them get corrupted and could not be used anymore. So what happened is that there is a program there in the centrifuge, right? That's rotating, right? So modify the execution of a program, right? I'm not saying that SNARK would solve that, but if we would have proof of execution for everything in the mission critical systems, that things are things are being executed, programs are running correctly, we could prevent many attacks. So this is, I think in future when we have more connected devices, more factories with systems that are connected to internet or connected to each other, this is very useful. This is like, I think we can mitigate many critical situations. So here in this scenario, these robots could be corrupted, and someone could actually modify the anomaly detection. You know, the weights of the model, there are some weights. They could just swap them, or like not taking into account some of the steps, some convolutional layers. Some of the steps could be like some activation function would not work correctly. But if you would use something like a SNARK, that if you run an inference on this model, or any program that this robot has to do, if you would have proofs, then we could verify that something goes wrong. If it says there is no anomaly, maybe another person could check the proof, say, oh, actually, you didn't run the anomaly detection correctly. I don't trust your input. So they could just investigate. So that can be a mechanism to be used. In Nokia, we're looking into that. So maybe we can enhance this. And the biggest challenge here is that generating these proofs are very compute intensive. So if you want to generate a proof here, these robots, I think all the computing capacity is going to be used for the anomaly detection, not to generate proofs. But this is a topic of research. People are doing PhDs, and research companies are working on this, not just on robots, but on improving the speed of proof generation. So this is a really active topic. Many people are working on it. So this brings me to zero-knowledge machine learning. So we can provide proofs for training. Like if you train the data, you can provide actually this data was trained using, this model was trained using data which was not copyrighted. Nowadays, I mean, we have this problem. We don't know this. There were a lot of issues, I mean, recently that people, I think Adobe or some company, they trained a lot of models for images that the pictures were not, they didn't have the copyright to do that, and they were not Creative Commons, for example. So you could have actually provide the proof next to a model that this model was trained with actual data which is allowed, particular data set. Or if you have an inference, you can provide the proof that I use the right and promised set of weights for my model inference. Yeah, as I think I explained the cyber attacks. But this is really active topic of research because AI typically, if you write this model inferencing, if you write the circuit of it, it's a giant circuit. So they have like trillions of constraints. Constraints are the rows in the matrix that you saw. For example, recently, I think some company in the US, the Llama model from Facebook, you know, the Llama model, I think you heard about it or not, it's an open source model. They wrote the circuit of that they had, I think it's over a couple of billions, or billions, I think, 24 billion, something like that, 24 billion constraints. And just think about the interpolation of that A that we wanted to do. I think you need to have huge amount of memory to just keep that polynomials that you saw in memory to be able to multiply them or do something. So this is crazy. So people are like inventing new ways. But this is like an application case, which is, you can fight disinformation with it. You can have like if you have a data online, you can have a provenance, like this data really came from an AI or it was really actual data. It's not solving the problem, but it's a way to do that. So people are looking into that. It's a very active topic. As I said, there is no math here, so you can step back and relax and listen to applications. So Polygon is a project. Anyone heard about Polygon? It's a blockchain project. So they have a solution for running a smart contracts. You know what smart contract is, you heard about it. Some programs on blockchain and generate the proof that this execution was done correctly is used for many things, whatever. But if you, in blockchain, usually the systems are decentralized. So anyone can run, be a miner or a validator or whatever. The system works with the masses. So it's decentralized. So anyone actually can run a ZK prover. And the requirement for ZK prover is 1 terabyte of RAM. So if you want to run a Polygon ZK prover, you need to have 1 terabyte of RAM. I never had that much RAM in my life. If you sum up all my laptops and computers, all of us maybe, it's like a lot of RAM. And then 128 core CPU. So who has that system? Because that's what they need to have a kind of comfortable working system to generate and provide proofs. So this is another dimension that people are working on. So one dimension is that people are saying that, okay, these robots that you saw in the previous picture can do the anomaly detection, has a computation trace, but the moment that he wants to really generate the proof, let's outsource this to the cloud or to somewhere else that there is resources. But then that's robots took a picture, but the picture is a factory side. It's like, or it can be in a concert or whatever. This is like either privacy sensitive data, which is in that computation trace, or business sensitive data. It can be they don't want to show what's going on in the factory. But you have to take this data, which involve all those sensitive data, send it to another computing infrastructure for proof generation. But that's why people look at multi-party computation, homomorphic encryption, that meaning that that robot would encrypt that computation trace for proof generation and send the encrypted computation trace, and somehow in the cloud, the systems that are accelerating a proof generation would magically do that with the homomorphic encryption. It's not our topic, but I just want to say that people are working on. There are some references to papers here. If you just search, Google them, you'll find them. The slides will be available if you're interested. It's a very active topic of research also. I mean, I had 1 or 2 master students doing master thesis also about this topic. It's an active topic I'm working on myself. There is another dimension to this. So people were thinking like, writing circuits are difficult, right? You will see, like composing your program into circuits and constraints and having gates. This is complex. They said that what if we use virtual machine paradigm? Like whatever program you write for this virtual machine, you're familiar with Java, JVM? You heard about it? So you program in Java, you compile it to bytecode, right? There is a VM here, which compiles your Java high-level code to bytecode. They say that what if you write program in Java, and you have this, but this is not about Java, I'm just giving you an analogy to understand. This JVM produced a code, produced a circuit for me. And Java has bytecode, so there's certain instruction sets there, we will write circuit for that instruction set. We just say how to compose the circuit somehow, as you can see. So you avoid having this high-level complex program. So whatever your virtual machine can execute will be accompanied with a proof in the end. So this program, give it to this VM, VM computes, provides you output, and also a proof. So this is a path that many people are working on. There are many virtual machines, and a number of them is RISC-0, Nexus VM, Jolts, P1. They're very active companies. They're all companies. Huh? They're not like random academic research. People are working on them, a lot of people. So soon we might have really usable virtual machines that, if they are fast, then there is no reason not to have the proof of execution for our daily computations. But what it does is that it has, a VM is like a hardware, like it's a computer, like it has memory, registers, I/O, whatever. So they make sure that all the values that come to registers, they are consistent with the code we give it to them. Like if we have to, our program, when it compiles to this instruction set of this VM, if it needs to read this address in memory and take this value, put it there, do something to it and put it back, they check that all this computation, all the memory accesses, IOs, whatever, they're consistent, they're correct. It's exactly based on what we gave it to them. This is how they provide proofs. This is the dimension. I just want you to know that this exists and people are working on it. But then in your program, you might have inputs like some values. And that, again, also is the zero knowledge part, that you can hide that. The proof doesn't need that to be verified. And you can say that there was a program executed with that input. And this is the proof for that. And you don't need to know the execution. So another thing is about fighting disinformation. So this is in fact deployed by Rolling Stone magazine. I will show you the link. We can go and see the proofs ourselves. So you see this picture. It's a random picture I found online, but there are like these examples that don't trust the media, but I just want to send a message. So you don't know what's going on in this picture. This is like published by a newspaper. You see this? I don't know what this guy did. He's really a bad person. But there's also this picture. But someone is actually giving water to that guy. But what is the gun? But then there's this picture. You know, there's someone, it's like, if you see this picture alone, you think they're helping him, but in fact, there's a gun pointing at his head. So which one to trust? We don't know, right? This picture, depending on what operation you do on the original picture, you crop it, you change the size, cut someone, you don't know. So this is like, you might say again, what is the relation to SNARKS, zero knowledge proof and whatever? You will see. Maybe I will, before telling it, I can tell you, let's see. Let me see what I say. Okay, now I will tell you what it is. So what we want to do here, we want to say that a picture comes from a camera. We want to make sure that certain allowed operations are done into this picture. Apparently some association of journalists somewhere, they define what are the allowed operations. Like if you have a picture, if you change the colors, make brightness a little different, is allowed. If you crop a little, is okay. Certain operations are allowed in their ethics guidelines or whatever. So if a journalist do this modification and ask you, okay, this is the picture and I just did that, how do you know that they really did that only? Right? Maybe they crop really in the middle, they cut out someone. So you don't know. But we want to create these provenance proofs. Provenance proofs are meaning that that final picture, when you get it, you know that it comes from an original picture taken by a camera in the location. And also, only, for example, the brightness was changed a little, nothing else. And this is the final picture with the proof. And that proof will tell you that only these things happen. So this is a way to fight this information. I'm not saying it solves it, but it's a way to, you can track a picture and say that, okay, this image was really taken in this location with this camera, and then only brightness was changed. So nowadays, most advanced cameras, they have signing keys in them. So when you take a picture, in fact, the picture comes with some metadata and the picture itself and a signature. So if you take all this metadata and content of the image, you can verify the signature. And it's signed by a key which is in the, I don't know exactly where the key is. There are some keys that is probably everyone can verify them. I don't know the details, I just want to give you the intuition. So the metadata are location, when the camera was taking a picture, the timestamp, and whatever the camera provides. So you do that. But you know, the photographers, I mean, if you are into photography, you're never happy with the picture. You always like tweak it a little, modify it, or you take it to Photoshop. Or photographers are crazy about this, so many of them. So what we want to do is that we want to verify the picture was not forged, and we want to know that the location and timestamps are there. I think the problem here, I'm not sure you notice it or not, the moment you change one bit in the picture, that can be nothing. Huh? Even you change the brightness, you change a lot, but even one bit, that signature doesn't verify anymore. Right? It's because the signature works with that content of data. So in fact, we are going to use the SNARK to solve this. You will see how. This is what I said. So any little modification, that signature doesn't work anymore. So this is the picture. Made it smaller. Same picture. We take it, and in the bottom we have a signature. We run these operations in a ZK SNARK. So think of it as a program we run that is verifiable. What we do in this program later, we can verify this. Every step of these operations were done honestly. So what we do is that first, we verify that the original signature created by the camera was correct. So we are sure. We modify the operation which is allowed on the picture. So we have a new picture which is green, like changing brightness or cropping a little. So the signature won't work anymore. So we have a new picture. We check that that operation belongs to the set of allowed operations. And we check that every single metadata of the picture is not changed with this line, like location, time, stamp, whatever, and we return the new picture. So this would give us a new picture with the proof. So you can throw away the signature. What the proof says that there was a signature from a known camera from Sony or Canon or whatever. That signature was correct, so the real camera took the picture, and the allowed operations were this, and the photographer modified only that much, and all the metadata are preserved. Nothing is changed. So this proof says this, and the proof is a SNARK, and we can quickly verify this proof. So the proof is say this. Proof is say that it comes from an original picture, picture was not changed, an allowed modification was done. And the location timestamp is the same. So, was it clear? I think simple. Or not clear? No? Zero feedback. Okay, but it's like fighting disinformation. This is used in a Rolling Stone magazine. I can show you actually. I mean, it's not for every post of a Rolling Stone magazine. What do you see? Okay. So there was a contest for innovation or something, and they incorporated this. I really don't know that every article has that type of things or not. But in fact, the original article is this, without the archive. It's about the war crimes in Bosnia. And then there are pictures here about Bosnia. And if you go to these pictures, when you open the article, you see a picture. Oh, there's this thing here. When you click, you will see all the provenance of this picture. But there are lots of other things, not just zero knowledge proofs. But this picture was taken, it is located on blockchain or somewhere, and then the format dimension, blah, blah, blah. The signature that I talked about, the signature already verified by some people. And see the crop and resize with Adobe Photoshop, sharpen with Adobe Photoshop, and there are the information. But this is not the zero knowledge one. Zero knowledge one are here, on the previous page. Here, this is for there's some political documents that they redacted some sensitive information from this for zero knowledge. Not for zero knowledge, because there were sensitive data related to those wars. They're leaked documents, I think. But then they provide a proof that this redaction was done only is what you see in the picture. It's not like a redaction more than what was supposed to be done. So they provide the proof that this was really coming from a real, actual document. And this is somewhere here, I think. zero knowledge proofs of redaction. But these are just like, you have to see what it is. Huh? But it's on the blockchain. The actual proof that you saw, we had the math, but the actual proof is on blockchain, but I don't want to click. But yeah, these things are real. I know you don't, probably you're overwhelmed with them, but people really use them. To be honest, I don't have a lot of content left, but I just wanted to show you how the tooling landscape is. If tomorrow you want to say that, okay, the math is complex, I don't care, but people developed them, implemented them. You can just right now write programs and provide proofs. I want to have proofs because maybe you can design something, you can have your startup later. I don't know, how can I program this? So this is how the ZK SNARKS software system look like. So typically there is a programming language, some domain-specific language, DSL, that you write your circuits, like to program it. There are many DSLs or programs called something like Circom, Socrates, Leuven, Cairo, Noah, many more. There are a lot. People are working on it. There are companies behind all these names. And then you compile this to some representation. We saw today together with these matrices, which was R1CS, but there are other representations and they have their own properties. Some of them are like, for example, in R1CS, our constraints are only the multiplications. Additions are for free. What it means doesn't matter, but there are different representations, different formats for this, different constraint systems. And then after that, so you have your actual circuit, you compile it to this middle representation, or arithmetization, we call it also arithmetization. Based on the circuit you have, you generate a proving key and verification key. You give it to a prover engine with your input. Witness is all the wire values. We give it to this prover engine, and then with X is your public input, and it provides you a proof. It's a very simple pipeline. So I want to show you Circom, the first one, how we can write a circuit with Circom. But Circom really took the concept seriously. So they really, when you program, it looks like a hardware programming languages. I don't know if you've ever worked with hardware programming languages. Me neither, if you haven't. But I just heard that this is really similar to hardware programming languages. So what in Circom, you write your program in a file, like your circuit.circom with the extension Circom. Then you compile it to R1CS, what you have seen, the matrices. You encode your program into these matrices. Then also you compile it to some assembly, something executable. But here, Circom supports WebAssembly, something that you can actually run the program, regardless of proving. So it compiles it to this WASP, WebAssembly. It's something that your computer, your browser can execute. I mean, if it's calculating an average or if it is model inference or whatever, you can actually execute this. So you execute and generate a witness. So if you execute the program, you have an output of that execution, which is whatever, some value. And also the witness, which is the input to this circuit, to this program. Some values you give as an input to the program to execute. And also the witness is all the wire values we had in that program. If it was a circuit, all the wire value, the vector S we had, if you listen to me. I don't know if you listened or not, but this was for execution. Now we have this representation, which those matrices. Now we want to, in fact, generate the evaluation key and a verification key, the proving key. But we wrote the math. But here is just the command. You say this is my circuit and this is my circuit, and just generate a proving key and a verification key. It's 2 keys. You don't care what it is. Just 2 keys that you can generate proof and one for verifying. Then you feed the result and the witness, all the vector S, all the wire values is a file. You feed it to the prover, and the trusted setup material, it provides you a proof. And then when you have the proof, later on, someone else, or yourself or someone else, preferably someone else, can verify, in fact, the proof is correct. It needs a verification key, of course, the proof, and also if your program had some public inputs, you can provide them. Your program can have no public inputs. Public input can be private key, can be some data set which is public, your program needs it or something, if it needs it. Pass or fail. So I want to show you a very mini program, which is about prime factorization. It's a very dummy program, but imagine we have two prime number. I know two prime number. I want to convince you that I know two prime number, specific ones. I give you the multiplication of them. In RSA, you have seen it, right? In two prime, big prime number, you multiply. Solving this factorization is very hard. But the little primes are your private key. It's part of your secret that you have. So I want to convince you, I know two big prime numbers. This is n. N is the multiplication of them. N is the public value. I give it to you and say, I know two big primes that are, if I multiply them, is equal to n. This is what I want to prove you. It's a very simple thing. So the goal is I want to produce a proof that I know a pair of P and Q such that n is equal to 923, without telling the verifier that P and Q are what they are, you know. But I knew in advance. Internally, I knew that there are 13 and 71. But assume that these are very big numbers, but they're not big, for example, because I wanted to see the values. If they're very big, it's a factorization problem, then in fact, it's not easy to find out what they are. So I will show you some code. In the slide, there are some links to the repository that I hosted this. You can always access it. So I thought we can write it together, in fact. Yeah, I will do it. You're seeing this one. Okay, this is because I prepared it in advance for myself. I thought I can write it with you. Then I thought, okay. Oh, I will not write it. I will just show you the code that I wrote. Okay. So it's in this folder. So I also prepared the image modification, but I couldn't finish it for the course. But it exists, you know. I wanted to show you how we can have an original picture and you crop something from it, but we won't have time to dive into that one. Okay, here's my mouse. Oh, okay. So as I said, everything is inside this. So this is a circum program. I have to look there because it's not mirrored. This is a circum program. As I said, in circum, everything is like really hardware, like gates. We have gates, we have ICs and everything like that. So this is a template. Template is like a class in Java, for example. A class, a struct in Rust, or something, some namespace in C++, something, C++. So I would say that this gate, or this component, this template, has 3 inputs. So think of it IC, think of program. This function, this component has 3 inputs, P, Q, and N. N is a multiplication of P and Q. I am the prover. I know P and Q and N. What I do is that I multiply P to Q, and I check that is equal to N. This is checking. If it's correct, it's perfect. If it's not correct, this program is crash. And this is how I instantiate this. So signal means that if you write this like a circuit, think of it as a circuit, these are the wire values. By default in circum, all wire values are private. But you could say that something is not private, something is public, by indicating it here. I'm saying that N is public because in fact N is something that I'm claiming, is a statement. I said this is N, I know 2 prime number. So I indicate it here. There's nothing special here, I just initialize this. So, is it maybe a bit smaller? Is better? Is it good still? Okay. Just want to run this. So when I run, what happens? So what happens is that I will give two inputs to this circuit. What I'm running is, in fact, generating a proof. So what you get is a proof, and to verify that, you only need to give n. But P and Q were in that program. And when I use 3 equals, means that this is a constraint added to that row of a matrix. If I would use something like this, it would create a constraint and it would add the value to n, but I don't want to do that. I'm just put some extra information I told you. But when I have 3 lines, means that the constraint will be checked. It will be really taken into account for proof generation. And this is what we want to check. We want to really check that the multiplication is equal to n. But there's a make file I prepared. It does everything for us. In a row, it creates a proof, executes it and generates a proof, and the SNARKS says that the proof is okay. But you can see what happened here. There are a lot of files appeared. Like the input to this proof was this. You can see I provided P, Q, N. This was there before. So I provided this to the input. And then this power P tau, these are like, if you remember the math, when I was explaining the setup time that we had all this bizarre G power of some things, this is all in this. And R1 sees is the matrices, but you cannot see it because it's in binary format. This is the witness, in fact. This is also in format you cannot see. This is the witness. This is the verification key. Verification key is using elliptic curve cryptography. This is the verification key. This is the PK, what is it? I don't remember. Okay. And I think this is our proof. This is the proof we have. And this is GROT16. GROT16 is a proof after Pinocchio. What I told you had 4 group elements. GROT16 has 3 group elements. This is the proof. For any size of program, the proof will be this size, something like that. And it verified it. Yeah. But the image modification, what I was preparing for you was something a bit bigger. So I was preparing cropping, the example with cropping. So imagine we have a picture. A picture is a lot of pixels in it, right? Each pixel is like RGB, like red, green, blue. So there are like 24 bits. Each of them are 8 bits. So each pixel, if you put all these pixels together, we have our image. So if we crop, it means that we just take a subset of these pixels and we grab that and we have that new picture. So what we have to check, for example, for cropping a picture is that these are all the pictures, the pixels for original picture. For me, check that for these coordinates, these pixels exist in the original picture in exact correct order. This code is doing that. It's taking the original height and weight. These are like, if you can see, is a very complex matrix and each element is like a 3 because it's like RGB, so the pixel is composed of 3 values. And we have the new one, the one which we crop. And here we are just checking for that coordinates that that thing is exactly in the same position. That the pixels are the same. I was preparing this, I didn't make it. But then for every pixel, it creates a constraint. So each constraint was a row in that matrix. So if you have a 20 megapixel camera, or you can see it's a lot of pixels. So the matrix will be gigantic. To generate the proof, you have to interpolate those polynomials for each of those columns. You would need crazy amount of memory to do that. I don't have the ballpark numbers, but it's crazy. This is something people are working. But it doesn't matter here. But this you would be able to compute this. But I couldn't prepare the inputs for this program to show you. Do you have a feeling for how to write the circuits? Or? But you could compute, or you could do more things. You can, where is my mouse? You could you could check other things, like if pixels or something, or even in this example, for primes, where is it? You could just continue programming here. You could just like program more things, check more things. For example, if this program was the ID card example, the input was the birth date and some information on the ID card. Here it would check that the birth date, it would calculate the age. Based on this birth date, the age is more than 18. And when you generate the proof, that birth date would be a private input. They would never see that. And then you could provide a proof, and that proof would be sent to some person who wanted to authenticate you. Yeah, something like this. I think we can wrap it up. Wait. Okay. There's some interesting circuits for image modification here if you want to see from this person, Trisha Datta from Stanford University, and also what you have seen about Prime and a little bit more in my own personal GitHub repository if you're interested. And there are a lot of references to learn more. I know this talk was very overwhelming in the afternoon. I see all of you are tired. But the topic is hot. I think now that you heard the terms, later on if you look at the job market, you will see there is a lot of very high-paying jobs in this area. But if you happen that you are interested, you want to learn more about it, I think the third option, ZK Learning, there are a series of videos that starting from nothing and going to really advanced topics. They teach everything. And it's taught by very famous professors. I recommend doing that. And there are some tools. Maybe we can wrap it up here. Do you have any questions or feedback or nothing? So it's time to go home then. I stopped.